All right, let's go. Number 10. The pixels that shouldn't exist in the fabric of reality. For over a century, physicists have assumed something quiet and fundamental about the universe we live in. They assumed it was smooth, continuous, that if you zoomed into any point in space, no matter how small, you would find more space, more matter, more detail, down to the level of quantum foam and beyond. That assumption is now under serious mathematical pressure. In June of 2026, a team of physicists at the University of British Columbia, Okanagan, published a paper that has quietly become one of the most discussed physics papers of the year. Using a framework combining Gödel's incompleteness theorem with modern quantum gravity, they demonstrated something that has long been suspected but never mathematically proven. The universe, at its most fundamental level, is not continuous. It is discrete. It is, in the language they used in the paper, pixelated, which sounds like a technical detail. It is not. Here is what it means. If you could zoom in far enough, past atoms, past protons, past quarks, past anything we have instruments to measure, you would eventually hit a wall, not a physical wall, a resolution wall, a point at which reality simply stops having any smaller pieces to describe. The universe becomes, in every measurable sense, a grid, a three-dimensional lattice of the smallest possible units of existence. This is called the Planck scale. It has been theoretically predicted for over 100 years, but until this paper, we had no rigorous mathematical proof that reality actually operates this way. Now we do, and here is the disturbing follow-up question that the researchers themselves have not quite been willing to ask in public. Everything we know that is pixelated is manufactured. Every image on your screen, every video you have ever watched, every digital representation of anything in human history is pixelated because we designed it that way. Continuous things in nature are not pixelated. Water is not pixelated. Sound is not pixelated. Time, until this paper, was not thought to be pixelated, but space itself now appears to be, which raises a question that used to belong entirely to philosophy and which is now beginning to slip into the domain of testable physics. If the universe has a resolution limit, if it is built out of the smallest possible chunks of existence, if it looks at the deepest scale exactly the way a computer simulation would look at the deepest scale, then how do we know it is not one? The answer before this paper was that we could not tell the difference. The answer after this paper is more complicated because the universe, whatever it is, has now been proven to have a property that no natural, continuous, spontaneously self-generating cosmos should have. It has been proven to have pixels. Number 9, the speed of light problem that shouldn't be a problem. Nothing in the known universe can travel faster than light, not information, not matter, not causation. Light itself, moving through a vacuum, travels at exactly 299,792,458 meters per second. Not faster, not slower, exactly that number, always, everywhere, forever. Every physics textbook accepts this as a fundamental law of the universe. Einstein's entire theory of relativity is built on it. Every experiment we have ever conducted has confirmed it. It is one of the most tested facts in all of science. But it is also, when you stop and think about it, a very strange fact. Why is there a speed limit at all? Why should the universe care how fast information moves? In a truly infinite, smooth, continuous cosmos, there is no obvious reason for such a limit to exist. Signals could travel instantaneously. Cause and effect could ripple through space without delay. Reality could update itself in real time everywhere at once, but it doesn't. It obeys a strict, unbreakable, absolutely universal maximum speed. In every other context we know about, speed limits exist for one specific reason. They exist because whatever is generating the movement has a maximum processing rate. Your computer has a processor speed. Your phone has a refresh rate. Every video game ever built has a frame rate, beyond which the game cannot update the world faster than the machine can compute. The universe, according to every measurement we can make, has exactly this behavior. It has a maximum rate at which information can propagate. It has a frame rate. Now, physicists have known this for 100 years, and most of them have shrugged. It is just how the universe works, they say. There is no reason to search for a deeper explanation. But in 2026, that shrug is becoming harder to maintain because as our tools improve, we keep finding more and more properties of the universe that look exactly like the properties of a computational system. A resolution limit, a speed limit, a maximum information density, discrete quantum states, observer-dependent behavior at the smallest scales. These are not coincidences. They are the fingerprints of a system that is being computed, not one that is simply being. And the speed of light, that beautiful, elegant, universal constant, may not be a law of nature. It may be the maximum clock speed of whatever is running us. Number 8, the experiment that says particles only exist when someone is looking. In 1801, a British scientist named Thomas Young performed what has become one of the most famous experiments in the history of physics. It is called the double-slit experiment. Every physics student in every country learns it, and every physics student at some point has to sit down and try to make peace with what it actually shows. Here is the setup. You have a light source. You have a screen with 2 narrow parallel slits cut into it, and you have a detector behind the screen to see where the light lands. If you shine light through the 2 slits, you would expect to see 2 bright lines on the detector, 1 line for each slit. That is what particles should do. They should go through one slit or the other, land where they were aimed, and produce 2 neat lines. That is not what happens. What actually happens is that you see many bright lines, alternating with dark lines, in a pattern called an interference pattern. The light behaves not like a particle traveling through slits, but like a wave, passing through both slits simultaneously and interfering with itself on the way out, which is fine. Light, we learned, is both a particle and a wave. Weird, but manageable. Then, in the 20th century, physicists tried the same experiment with individual electrons, solid, discrete particles, sent through the slits one at a time. The electrons still made an interference pattern, which means that each single electron somehow was passing through both slits at once, interfering with itself and landing on the detector as part of a wave. This should be physically impossible. An electron is a particle. Particles are discrete. Discrete things do not pass through 2 doors at the same time. The physicists, understandably, wanted to check, so they set up a detector at the slits themselves. They wanted to see which slit each electron actually went through. The moment they did that, the interference pattern disappeared. The electrons started behaving like normal, well-mannered particles. Each one went through exactly 1 slit, 2 clean lines on the detector, perfectly ordinary. The physicists removed the detector. The interference pattern came back. They put the detector on again. The pattern vanished. They repeated this in different labs with different setups, thousands of times, for over a century now. The result is always the same. When nobody is measuring which slit the particle goes through, it goes through both. When someone is measuring, it picks one. The universe, at the smallest scale, appears to change its behavior depending on whether it is being observed, which is again an extremely strange fact to have to live with. In no other context in nature do we see this. A tree does not stop being a tree when you close your eyes. A river does not freeze when the camera turns off. Only at the quantum level, only when we look at the fundamental building blocks of reality, do we find that the act of observation changes what is being observed. There is a name for this. It is called the measurement problem, and it has been the deepest unsolved question in physics for over 100 years. But there is another interpretation, and it is the one that has begun quietly gaining respect among the physicists who take simulation theory seriously. In every video game ever built, there is a technique called occlusion culling. The game engine does not render what the player cannot see. If you turn your camera away from a wall, the wall does not exist as a fully computed structure. It is just data. It only becomes visible, only becomes computed when you look at it. The universe at the quantum scale appears to behave exactly this way. It renders when observed. It exists as unrendered probability when it is not, and no natural, physical, non-computational reality has any reason to work like this, but a rendered one does. Number 7, the collective memory glitch millions of people cannot explain. In 2010, a paranormal researcher named Fiona Broom coined a term for something she had noticed. She was talking to a group of colleagues at a conference, and the conversation turned to Nelson Mandela. Broom remembered clearly that Mandela had died in prison in the 1980s. So did the people she was talking to. So did thousands of other people online, except Nelson Mandela had not died in prison in the 1980s. He was still alive in 2010. He would live until 2013. Broom called it the Mandela effect, and in the 15 years since she named it, researchers have documented hundreds of similar cases. Millions of people misremembering the same specific detail about the world, not vaguely, specifically, in identical ways, about things they should have no reason to misremember. The cartoon Berenstain Bears, which many people remember as Berenstein Bears, with an E, the Monopoly Man, who most people remember wearing a monocle, though he does not. The line in the film Snow White, remembered as Mirror, Mirror on the Wall, though it is actually Magic Mirror, the fruit of the Loom logo, remembered by millions of people as including a cornucopia, though it never has. The conventional explanation is that these are all just false memories. Human memory is unreliable. People misremember things all the time. When many people misremember the same detail, it is because we share cultural cues that lead us to fill in the same wrong answer. This explanation is probably correct in most cases, but it does not fully account for the specificity of many of these examples, or for how thousands of people in different countries, in different age groups, with no shared cultural exposure, can independently generate the same exact false memory about the same exact detail. Which is why, in the last few years, a smaller but growing group of physicists, philosophers, and simulation theorists have started proposing a different interpretation. What if the world was updated? What if, somewhere in the process that generates the reality we experience, small details are occasionally being adjusted? Not maliciously, not deliberately, just as part of whatever ongoing computation the universe is performing. And what if, in rare cases, some fraction of the population remembers the state of the world before the update, while the rest of the world reflects the state after? There is no way to prove this hypothesis. There may never be, but the pattern it describes matches the observed data more precisely than the traditional false memory explanation does. And the more we learn about how universes might, in principle, be computed, the harder it becomes to dismiss. Something is producing these memories. Something is producing them at scale. And whatever is producing them does not fit cleanly into our current model of a single, stable, continuous reality. Number 6, the cold spot in the sky that shouldn't be there. The cosmic microwave background is one of the most important discoveries in modern astronomy. It is the leftover heat from the Big Bang, a faint glow of radiation coming from every direction in the sky, permeating all of space, carrying an imprint of what the universe looked like about 380,000 years after it began. For decades, cosmologists have mapped this background radiation with increasing precision, and it has always shown almost exactly what the standard model of cosmology predicts. A nearly uniform temperature across the entire sky, with tiny, random fluctuations at the level of 1 part in 100,000. Exactly what you would expect from a smooth, homogeneous early universe. Almost exactly. There is one region of the sky where the pattern breaks down. It is called the cold spot. And it is a problem that the field has been quietly trying to explain for over 20 years. The cold spot is a large region of the cosmic microwave background, approximately 1.8 billion light-years across, that is significantly colder than the surrounding sky, not slightly colder, distinctly, statistically, undeniably colder, by a margin that has resisted every attempt at conventional explanation. According to standard cosmology, this region should not exist. The early universe was uniform. Any large-scale temperature variations should follow the pattern predicted by inflation theory. The cold spot does not follow that pattern. It is anomalous. It is what physicists diplomatically call an outlier. Multiple explanations have been proposed over the years. Perhaps it is a giant supervoid, a region of the universe with fewer galaxies than average, cooling the light that passes through it. But the supervoids we can measure are not big enough to fully account for the temperature temperature difference. Perhaps it is a statistical fluke, the rare kind of random anomaly that shows up in any large enough dataset, but the statistics do not support that either. The probability of a fluctuation this large occurring by chance is small enough that most cosmologists have stopped taking it seriously as an explanation, which leaves the interpretations that require modifications to fundamental physics. Some theorists have proposed that the cold spot could be the imprint of a collision between our universe and another universe in a hypothetical multiverse. Others have suggested it could be a topological defect from the earliest moments of cosmic history, and a small but persistent minority of researchers have offered the interpretation that keeps appearing in these discussions. The cold spot could be a glitch, a region of the sky where the underlying computation of the universe produced an error, a rendering failure, a place where whatever is generating the reality we see failed to fill in the correct temperature and left behind a signature that is, on any natural explanation, statistically almost impossible to justify. Number 5, the 26 numbers that had to be perfect. Modern physics can be summarized at its foundation by a set of 26 numbers. These numbers are called the fundamental constants of nature. They include the mass of the electron, the strength of gravity, the fine structure constant that governs how light interacts with matter, and about 20 others. Each of these constants has a specific measured value, and here is the disturbing part. If any of these values had been even slightly different, the universe as we know it could not exist. Not a little different, slightly different. If the fine structure constant were 4% larger or smaller, stars could not produce carbon through nuclear fusion. Without carbon, there would be no organic chemistry. Without organic chemistry, there would be no life. If the strength of gravity were slightly stronger, stars would burn out too fast for planets to form and biology to develop. If gravity were slightly weaker, matter would never clump together into galaxies at all. If the mass of the neutron were slightly higher than the mass of the proton, atoms as we know them would decay in fractions of a second, and the universe would be filled with nothing but radiation. If the ratio were slightly different in the other direction, no stable atoms would form. Every single one of these 26 numbers appears to be finely tuned to permit the existence of complex structures, stable chemistry, and eventually life. Not one number, not two, 26 of them, all simultaneously precise to a degree that is difficult to explain by chance alone. This is called the fine-tuning problem, and it has haunted physics for decades. 3 explanations have dominated the discussion. The first is that we simply live in a lucky universe. Out of all possible universes, we happen to inhabit one where the constants align to permit life. This is called the anthropic principle. It is philosophically weak because it does not actually explain anything. It just points at the fact and moves on. The second explanation is the multiverse. There may be countless universes, each with different values for the fundamental constants. Most of them are lifeless. Ours is one of the rare ones that happens to work. This is popular in modern cosmology, but it has one significant problem. We cannot observe other universes. We can only theorize about them, which makes the multiverse explanation technically outside the reach of empirical science. The third explanation is the one that used to be considered outside serious discussion, and which has, in the last several years, quietly returned to the table. Designed universes have finely tuned parameters. Every video game ever built has physical constants that were chosen by the developers to make the game work. Every simulation ever run has parameters set by whoever wrote it. Universes that arise spontaneously, without any designer, without any intention, are not expected to have parameters that permit complex structures at all. Random universes are almost certainly dead ones. We do not live in a dead universe. We live in one that appears to have been calibrated at the moment of its creation to permit exactly what we see. This does not prove the universe is a simulation. It cannot prove that. But it establishes something else. Fine-tuning is one of the specific signatures we would expect to find if we were living inside a designed system. And we find it. We find it in 26 independent parameters all at once, in a way that pure randomness has significant trouble explaining. Number 4, the phenomenon that carries information faster than light. Quantum entanglement was first described by Einstein, Podolsky, and Rosen in 1935. They did not describe it because they believed in it. They described it because they thought it proved quantum mechanics had to be incomplete. Einstein famously called the phenomenon spooky action at a distance, and he spent much of his later career trying to prove it was impossible. He was wrong. Quantum entanglement is real. It has been experimentally confirmed thousands of times. In 2022, the Nobel Prize in Physics was awarded specifically for the experiments that made the reality of entanglement undeniable. Here is what it is. When two quantum particles interact in the right way, they become entangled. From that moment forward, their properties are linked. If you measure a specific property of one particle, the corresponding property of the other particle is instantly determined. Not eventually determined, instantly. Even if the two particles have been moved to opposite ends of the universe, change the state of one, and the state of the other changes at the same moment, not after a delay proportional to the speed of light traveling between them. At the same moment, this should be impossible. Nothing in the standard model of physics can travel faster than light. Information cannot propagate instantaneously. Cause cannot precede effect. And yet, in every entanglement experiment ever performed, the correlation between the particles updates faster than any signal could possibly cross the distance between them. Physicists have spent nearly a century trying to make sense of this. Most modern interpretations argue that no actual information is being transmitted, that entanglement is a statistical correlation rather than a causal connection, and that no faster-than-light communication is truly occurring. These interpretations work well enough as mathematics. They work considerably less well as a description of reality. Because in every simulation ever built, in every computational system ever designed, we know exactly how to produce this behavior. If two variables in a program are pointing to the same underlying data structure, then changing one instantly changes the other, regardless of how far apart their visual representations appear on the screen. There is no delay. There is no propagation time. The two things look separate, but they are actually the same object being displayed in two locations. Quantum entanglement, in every observable way, matches this behavior exactly. Two particles that look separate, that are, at the level of their underlying description, the same object, that respond as one even when displayed in different places. There are natural interpretations of entanglement that do not require simulation theory. There always will be, but the fact remains that our universe contains a phenomenon which cannot be easily described by the physics of a continuous cosmos, and which can be trivially described by the physics of a computed one. Number 3, the philosopher who calculated the odds. In 2003, an Oxford philosopher named Nick Bostrom published a paper titled, "Are You Living in a Computer Simulation?" It was not a science fiction essay. It was a rigorous logical argument laid out in the style of a mathematical proof, and it has become one of the most cited philosophy papers of the 21st century. Bostrom's argument, in simplified form, goes like this. If any civilization in the history of the universe ever develops the technology to simulate a conscious reality, and if any such civilization ever decides to run such simulations, then it will almost certainly run many of them. Thousands, millions, possibly infinitely many. Which means that in any universe where technological civilizations exist and simulations are possible, the number of simulated realities will vastly outnumber the base reality. There will be one true universe and countless simulated ones. If you are a conscious being living inside such a universe, and you have no way to distinguish between base reality and a simulation from the inside, then statistically, you are almost certainly living in a simulation. Not because we have evidence for it, but because the ratio of simulated conscious beings to base reality conscious beings in any universe where simulations are possible is enormous. Bostrom's argument has 3 possible outcomes. Either technological civilizations always go extinct before developing the capacity to simulate reality, or such civilizations exist but never choose to run simulations, or we are most likely living inside one. The first 2 possibilities require assumptions about the behavior of every advanced civilization that has ever existed and everyone that ever will throughout the entire history of the universe. They are possible, they are not particularly plausible. The third possibility, that we are inside a simulation, is what the argument implies statistically, and it is what most careful readers of Bostrom's paper have concluded is the most likely of the three options. Elon Musk, in a public appearance in 2016, said that the odds we are living in base reality are, in his estimation, 1 in billions. Neil deGrasse Tyson has said publicly that he suspects the simulation hypothesis is more likely than not. Multiple physicists have quietly said the same thing in interviews. None of this is proof, but the argument itself is not easily dismissed. And in the years since Bostrom published his paper, it has moved from the fringes of philosophy to a topic that serious physicists now discuss without embarrassment. The universe may not be what it appears to be, and the statistics, if we take them seriously, suggest that it probably is not. Number 2, the proof from November of 2025 that the universe is not what anyone expected. On November 10th, 2025, researchers at the University of British Columbia, Okanagan, led by Dr. Mir Faisal, published a paper that made international news within 48 hours. Its title was measured and academic. Its implications, once translated out of the technical language, were profound. Using Gödel's incompleteness theorem combined with modern quantum gravity frameworks, they mathematically demonstrated that the universe cannot be a computer simulation, which sounds, on the surface, like the answer to the question, case closed, we are not simulated, except when you read the paper carefully, what they actually proved is stranger than a simulation would have been, because they did not prove that the universe is a normal, physical, computational cosmos. They proved that the universe requires a type of understanding that lies beyond any algorithmic system, that its foundations exist beyond the reach of computation itself. That reality is built on what the paper calls non-algorithmic understanding, a form of comprehension that no computer, no simulation, no computational system of any kind can produce. Read that again, slowly. The universe is not simulated, but it is also not the kind of thing that any computational system could have generated. It is something else, something for which we do not yet have a good word. Every material system we understand is either physical or computational. Physical systems are made of matter and energy, obeying the laws of physics. Computational systems are made of information, obeying the laws of algorithms. These are the only two categories our science has ever recognized. The UBC paper claims the universe fits into neither, which means the universe is either the first known example of a third kind of thing, some category of reality we have not yet named, or it is a thing whose actual nature is fundamentally hidden from any observer inside it. There is a name for entities whose nature is fundamentally hidden from observers inside them. There has always been a name for this. It is the definition of what religious traditions have called the divine, and what philosophical traditions have called the noumenal, the thing in itself. The UBC paper does not use these words. It cannot. It is a physics paper, but the space it points to, the type of reality it describes, is exactly the space these traditions have always occupied. Modern physics, in November of 2025, quietly took a step toward a conclusion it had spent a century trying to avoid. Reality may not be what any of our models of reality have ever been able to describe. Number 1, the theorem from 1931 that quietly explains everything. To understand the final and most disturbing item on this list, you have to understand a mathematical result from almost a century ago. It is called Gödel's incompleteness theorem, and it is arguably the most important discovery in the history of mathematics. In 1931, a young Austrian mathematician named Kurt Gödel proved something that no one had believed possible. He proved that any mathematical system rich enough to describe basic arithmetic must contain true statements which cannot be proved within that system. Let that settle. Truth in mathematics is not the same as provability. There are things that are true which no mathematical system can ever prove, not because we have not tried hard enough, not because our techniques are inadequate, because the very structure of formal reasoning has a fundamental limit built into it. Gödel's proof did not just describe a curiosity. It changed the philosophy of mathematics forever. It killed a project called Hilbert's program, which had aimed to reduce all of mathematics to a complete and consistent formal system. Gödel demonstrated that no such system can exist. ever for any topic, in any language. For decades after his proof, mathematicians treated this as a purely internal result, something about mathematics itself with no obvious implications for physics or philosophy or reality. That understanding is now changing because Gödel's theorem, at its deepest level, is not really about mathematics. It is about any system that operates by rules. It is about the limits of what rule-based reasoning can ever achieve. And in the century since it was proved, physicists have gradually come to realize that if the universe operates by rules, then the universe must be subject to the same limits. The UBC paper we discussed in item number 2 makes exactly this argument. It uses Gödel's theorem to demonstrate that if reality is computed, if it operates by any algorithmic process, then it cannot fully understand itself. There will always be truths about reality that reality itself cannot access. There will always be gaps. And in those gaps, in the spaces where the rules of any possible simulation break down, we would expect to find the same signatures we have been discussing throughout this video: anomalies, glitches, cold spots, fine-tuning that no rule-based system can explain, fundamental constants that had to be set by something outside the system, every strange fact about our universe, every one of the 10 items on this list, every deep unresolved question in physics fits more or less into the pattern that Gödel's theorem predicts we would find if the universe is any kind of rule-based system operating at any level of computational complexity, which brings us to the final and most disturbing implication. If the universe is computed, Gödel's theorem tells us there will always be truths it cannot express. If the universe is not computed, the UBC paper tells us it must be something for which we do not yet have a name. Either way, the reality we inhabit is not the simple, physical, self-explanatory place our common sense insists it is. It is either an incomplete simulation or it is a category of existence that lies fundamentally beyond our comprehension. There is no third option that our current mathematics permits. The universe you are experiencing right now, as you watch this video, is either a program with limits that cannot be seen from the inside, or it is a mystery that cannot be explained by anything computational at all. And that senior astronomer some of you asked me about, the one who allegedly said, off the record, that he wished we had never looked, the one who kept coming up in the comments after my last video, he was not talking about a black hole discovery. He was talking about the paper from November of last year, the one that quietly proved that the universe, in the deepest possible sense, is not what any of us have been assuming it to be. And once you know what that paper actually says, once you sit with it long enough, you begin to understand why he said it. Because there are, in this field, certain conclusions that once seen cannot be unseen. If any of these 10 discoveries kept you here to the end, if number 1 landed the way it landed for me when I first read the proof, then you should know something. There are older items I did not include on this list. Things from the 2000s and 2010s. Discoveries that never made mainstream news, that got buried in obscure journals, that pointed toward exactly the same conclusion this video has been building toward. I made a video about those. It is on the screen right now. If this one kept you up, that one will keep you up longer. And if you want to be here the moment the next major discovery drops, hit subscribe, because the papers describing the deep structure of our reality are being published faster now than at any point in the history of physics. And the next one, based on what is already circulating in the field, is going to be the most difficult one yet. All right, see you in the next one.